So before I begin, there is an article related to this video that you can read at this address, 0to-hero-dev SPIRE Rocks. And if you are new to the concept of security and trust and SPIFFE SPIRE and X509 certificate chains, I highly recommend you to read that article first before watching this video, because the article covers fundamental concepts and terminology that will be really useful when you follow this video. So okay, we can dive into the demo right away. In this demo, we are going to install SPIRE onto our cluster. And then we'll create a sample workload and make the workload talk to the SPIRE server to fetch some SWITs. And SWITs are like glorified X509 certificates that the workload can use to initiate things like, I don't know, signing identities or MTLS, mutual TLS connections, and talk to other workloads securely and stuff like that. And to begin, I need to create a special namespace for the SPIRE to install the SPIRE agent and the SPIRE server to our cluster. So first, let's check the namespaces that we have with a kubectl get ns. And yes, I don't have a SPIRE specific namespace right now. And this fizz namespace is the namespace that I keep my production workloads. And after deploying the SPIRE server and the SPIRE agents to a SPIRE namespace, we are going to deploy a sample workload to this fizz production namespace as well, and make sure that our sample workload can get SWITs, which are X509 certificates, like I said, into itself so that it can communicate to other services essentially. So what are SWITs again? SWITs are special X509 digital certificates that you can use to establish service-to-service secure communication channels. I'll create a namespace, but before that, let me write down what we are going to accomplish in this video so that I don't forget anything essentially. First of all, we are going to create a Kubernetes namespace, like I said. Then we'll create service accounts, cluster roles, and cluster role bindings that our SPIRE server needs, followed by doing the same for the SPIRE agent. Then we are going to deploy the actual SPIRE server as a Kubernetes stateful set. And after that, we are going to deploy SPIRE agents as Kubernetes daemon sets. Then we are going to configure a registration entry for our workload on the SPIRE server so that the workload can obtain an identity by proving that it is what the SPIRE server thinks it is by matching its attributes to the registration entry that we created in the previous step. Finally, we'll deploy our workload and shell into the workload. And the workload is nothing but a container inside a pod anyway. So quote workload is just a fancy way of saying containers essentially. So we'll shell into our workload container and then fetch some X509 certificates from the SPIRE agent. So yes, there's a lot to do. So let's get started, shall we? I'll start by creating a SPIRE namespace using kubectl create ns SPIRE. We'll initialize the manifests for the SPIRE server and the SPIRE agent into this namespace. We'll create a service account for the SPIRE server to use using this YAML. And in a deployment such as this, where the agent and server share the same cluster, SPIRE can be configured to automatically generate these certificates on a periodic basis and update a config map with contents of the certificates that it generates. And to do that, the server needs the ability to get and patch a config map object in the SPIRE namespace. And to enable that, we are going to need to create cluster roles and cluster role bindings that will allow our service account of the SPIRE server to modify this config map. So when we assign the cluster role you see here with a cluster role binding to the SPIRE server's service account, then the server will be able to populate this SPIRE bundle config map for the SPIRE agents located on the cluster to consume. Aside from this SPIRE bundle config map, the SPIRE server uses another config map to configure itself basically. So in that config map, there are initialization options for the server itself, such as where to open the Linux domain socket on the host, which volumes to mount on the server, and a bunch of other stuff. I'll just highlight a few key points that you might miss maybe, and leave the rest of the config map for you to read and research at your own convenience. Firstly, we are using this example.org as our trust domain, And since I'm using FizzBuzz Pro as part of my SPIFFE IDs in other parts of the installation that you'll see, this kind of discrepancy will cause us some trouble down the line, but I just wanted to keep it as it is to demonstrate you how an unsuccessful agent setup might look like and how you can troubleshoot and fix it, which is like these kinds of distributed deployments don't always go like ponies and rainbows. There will be always some curveballs. So it's always useful to know and see how you can diagnose such a situation. I've added my cluster name here into this node attester configuration, which is fizzcluster-v2, which is the name of my EKS cluster that I use. And if you are following along with me, make sure that you update this document and add the name of your cluster to it as well, because your cluster name will likely be different than mine. I have also enabled this token review API validation since my cloud provider, Amazon Web Services, supports it. And by default, this is false. So check your environment before enabling it. But enabling this check, if it is supported by your cloud provider, is highly recommended because it will enhance the security posture of your Spire server. And here are the liveness and readiness endpoints that might be useful to know about. And now let's apply the Spire server service account, bundle config map, cluster role, and cluster role binding to our cluster with this kubectl apply command. Okay, those are created. What next? Since we have the roles and dependencies we need in place, we can install the Spire server onto our cluster. We'll apply the Spire server config map that we mentioned a moment ago, and also we'll apply this Spire server stateful set. And again, let me highlight the important pieces in this stateful set configuration. And of course, you can check out the rest of the source code at your own comfort by checking the resources section linked at the end of this video's webpage. For example, this run Spire data folder is a persistent volume claim template that is mounted to this volume on the container using this Spire-data volume claim template, which means that the data will be persisted even if the pod that owns that volume is deleted and recreated. Then we have a service definition that exposes this Spire server over this gRPC port. I'll add that too with -f Spire server service YAML to the list of files that I am going to apply, and then press enter to create these three API objects: the Spire server config map, Spire server stateful set, and Spire server service. And that's all there is about the Spire server setup. Now let's do the same for the agents as well. But before that, I'll double check that our Spire server stateful set is up and running by doing a kubectl get stateful set -n Spire. I'll also check and verify that our Spire server service endpoint is up and running as well. Kubectl get service -n Spire. And we see that our service is up and running as well. Now that our server is configured, it's time to bring up the agents as well. We'll follow an almost identical process to initiate the agents. Again, for the agents, we have a cluster role and a cluster role binding that will give it read access to certain Kubernetes resources. And as with any cluster role, we have also a cluster role binding, as I said. And we'll use that cluster role binding to bind that cluster role to a service account, and that service account will be linked to a pod template. And this is a service account, nothing fancy actually, and this is the cluster role that we viewed before, and that's the cluster role binding. Let's apply the service account, cluster role, and cluster role binding trio to begin setting up our agents. And they are created. Now it's time to provision the actual agents. And like I said, since the agent is a daemon set, there will be one agent per Kubernetes node, and the agents are configured by using this agent config map that you see here. I'll again highlight the important pieces. For example, the trust domain is set to fizzbuzz.pro instead of the default, which was example.com, and that will cause us some troubles that we'll see down the line. Again, these are health and liveness probes that the agent daemon sets will be exposing. And here is the Spire agent daemon set manifest, which will do the actual heavy lifting of distributing the certificates and managing them, rotating them, expiring them, and stuff like that. And the agent will expose a domain socket under this run SPIRE sockets folder, which is statically linked to a folder on the host machine. And the host machine is our Kubernetes worker node in our cluster. And if you remember from the agent config map, the run SPIRE sockets agent sock is the Linux domain socket that the agent will be exposing for our client workloads to listen to. So let's apply the agent config map and the agent daemon set, which will complete the provisioning of the SPIRE agent on our cluster as well. And yes, the config map and the daemon set have been created too. Next, we'll install a workload onto a different namespace and then try to fetch X509 SWIT certificates from the SPIRE agent into this workload by using the SPIRE agent's workload API. But before that, let's make sure that the SPIRE agents are up and running in the first place. So to check it, I'll do a kubectl get daemon set -n SPIRE, which will give us 2 agents as expected. And since this is an EKS Kubernetes setup with 2 worker nodes, I was indeed expecting 2 agent daemon sets, and it looks like I have them, so that's all good. And when I do a kubectl get pow in the SPIRE namespace, I get 1 pod for the server and 2 pods for the agents, and that's also what I was expecting actually. And I'll wait for a while for these pods to bring up all of their containers to a ready state. But for some reason, my agents are not fully starting up. They are still not ready. And if you recall that I mentioned that we were using example.org as our trust domain in the SPIRE server config map, whereas our SPIRE agents were expecting fizzbuzz.pro, not example.org as our trust bundle root. And that might be a problem, and that might be a reason that the agents are not booting up. So let's check the logs of the pod to see if that's the case. Kubectl logs, and then I'll pick the name of one of the agents and pass SPIRE as the namespace. And we see the error message indicating that the agent cannot find a trust bundle for the domain example.org, which is expected because we configured our trust domain to be example.org, but we are matching it against fizzbuzz pro. So the fastest way to fix this is to update the manifest that still has example.org in it and rename example.org to fizzbuzz pro, then delete the SPIRE namespace, which will delete all of the servers and agents, and then do a fresh SPIRE server and SPIRE agent installation once more. So let's do that. I'll first search for example.org across the entire project, and I'll replace all of the occurrences of it with fizzbuzz pro. And it looks like I only have one missing here at the server conf, and I'm going to rename it to fizzbuzz pro. And let's delete this SPIRE namespace and then apply all of the server and agent manifests once more from scratch. So to do that, I'll do a kubectl delete namespace SPIRE, and then do a kubectl get ns to make sure that the SPIRE namespace is actually gone for good. Then I'm going to create the namespace again, kubectl create ns SPIRE. Then we'll create the SPIRE service account, bundle config map, cluster role binding again. Then I'm going to apply the SPIRE server config map and server stateful set and server service like we did in the first time. We'll wait for the SPIRE server stateful set to be ready and available, and then we'll begin installing the agents as we did before. First, I'm going to create the agent service account, cluster role, and cluster role binding again. Then we are going to deploy the agents by applying the agent config map and the agent daemon set. And once we query the daemon sets by doing a kubectl get daemon set -n SPIRE, we'll see that 2 SPIRE agents are available and ready. Though before being able to assign SWITs to workloads through these agents, we have 2 remaining things to do. First of all, we need to create a new server registration entry for the node that the server is on, specifying a SPIFFE ID to allocate the node. And note that we specify -node as a command line flag to indicate that we are registering a node and not an agent here. And we specify the cluster name, the namespace, and the service account as selectors to help the node attestation process. So let's execute this command. And next we'll do the same for the workloads. We are going to create a new registration entry for the workload, specifying the SPIFFE ID to allocate to the workload. So our workload will be using the SPIRE agent, and it is registered with this SPIFFE ID to the SPIRE server. And how do we identify this workload? by workload attestation selectors. So to attest that workload, we'll specify that it has a namespace fizz and a service account default. So any workload that match these criteria will be identified as our client workload and will be linked to this SPIFFE ID. So let's copy this command and execute it as well. And that went well too. So now let us install our client workload. And here is the deployment manifest for the client workload that we are going to use. So note that we are mounting this run SPIRE sockets folder to our workload pod as a volume. And this run SPIRE sockets folder is the folder where our SPIRE agent has an open Linux domain socket listening for incoming clients. And our workload will be one of those clients as well. We'll shell into our workload and talk to the domain socket from within our workload and try to list some SWITs that have been assigned to the workload. But before that, we need to deploy our workload. So let's deploy the client workload to the cluster by doing a kubectl apply-f spire client deployment YAML. And okay, let's get the name of our client pod. Then shell into it by doing a kubectl exec-it, the name of the client pod --bin sh. So we are in the client pod right now, and we can talk to the SPIRE agent's domain socket from within this workload container, because we have this op spire bin SPIRE agent binary that can actually communicate with that domain socket. So we'll execute opt spire bin SPIRE agent fetch socket path run spire socket agent.sock, where SPIRE agent is the binary that we can use to talk to the SPIRE agent daemon sets workload API on the cluster. And that workload API is exposed through a domain socket, like I said, and run SPIRE socket agent.sock is that domain socket that this SPIRE agent is listening to on this host machine, which is our Kubernetes worker node. And when we execute the command, we get a list of SWITs, and that means that our workload was able to fetch the X509 certificates, and with those certificates obtained, it now can establish a service-to-service secure communication channel with other SPIFFE-enabled workloads. And that concludes our demo. In the next video, we'll bring this setup into practice, and we are going to establish a secure mutual TLS or MTLS connectivity between IDM, crypto, and mailer microservices that we have in this deployment by assigning them SWITs and using the Go SPIFFE library to establish that communication. But as far as setting up SPIFFE and SPIRE on our EKS cluster, that's all there is to it. Until next time, may the source be with you.